We discovered in the first video that the CPU interacts with input and output devices, and that three of the components of the CPU are the control unit, the arithmetic logic unit, and the registers. Data is then transferred between each of these components and other devices along wires called buses. This design comes from an early computer scientist called John von Neumann, a Hungarian-American mathematician. His arrangement of the CPU and the way that it works, referred to as its architecture, has remained largely unchanged, the main difference being the addition of the cache to speed up its operations. In von Neumann's day, all program code and data that the CPU needed to access was stored in RAM. Von Neumann's design enables the CPU to run programs using the Fetch-Decode-Execute cycle. Let us rearrange our diagram so that we can explain this clearly. Originally, lines of code and data were stored in RAM ready to be called upon by the control unit. We'll bring our model up to date and move these into the cache, which is a part of the CPU. Next, we need to list some of the key registers that are involved in the Fetch-Decode-Execute cycle. They are the program counter, the memory address register, the memory data register, and the accumulator. Then we'll add some lines of code and data to the cache. Each line of code or piece of data is stored at a specific address. When a request is received to run a program, the control unit will initialize the program counter so that it can keep track of which instruction it needs to fetch from memory next. In our example, this is the instruction at memory location 01. The CPU will now store this address in the memory address register. It will then fetch the instruction at this address and put it in the memory data register. The control unit now decodes the instruction. Every type of CPU has a specific set of instructions, and the control unit looks at the instruction in the memory data register and carries it out. In this case, the control unit will load the data at address 05, placing it in the accumulator. The instruction at address 01 has now been decoded and executed, and so the program counter will be advanced to address 02. This address will be placed in the memory address register, and the instruction at 02 will be fetched to the memory data register. This instruction is now decoded. It requires the data at address 06 to be subtracted from the data in the accumulator. This will be done by the arithmetic logic unit, and the result put in the accumulator. Now that this instruction has been executed, the program counter will be advanced to address 03. This address will be placed in the memory address register, and the instruction at 03 will be fetched to the memory data register and decoded. When this instruction is executed, the value in the accumulator will be stored at address 07. This particular sequence might be followed by a halt instruction, or it might be followed by further calculations or decisions that need to be made by the ALU. You might think that the program counter is unnecessary, as its value is the same as the memory address register. However, very few programs are sequential, with code either being repeated in a loop or having jumps to other addresses depending upon the decisions made by the ALU. It is the job of the program counter to keep a track of these movements through the code so that the correct address is put into the memory address register. In a modern CPU, this fetch, decode, execute cycle will be carried out billions of times a second.